Hi guys, welcome to the first lecture that we're going to be taking notes on. Again, I just want to reemphasize that I'm going to be giving you information and I'll be saying write this down, and I don't want you to just turn in the raw notes. I want you to go back, get into the module with information that you need to put in there and quote, make it really good. And remember, you're creating a set of notes that you will be using to take your tests. So the more time that you put into this now, the less you'll have to worry about studying, and you'll know this material really well. Okay, so we're gonna share the screen here, and I'm gonna begin. This is the weather module, basic weather processes. So this is the one that says 2008, and I'm going to the print version. So we're gonna talk about a couple things. We're gonna be dealing with things in the atmosphere. Very simple, it's a very thin layer of what covers the Earth. And here's an interesting diagram that I want you to include in your notes. And you can look at the temperature profile of the atmosphere on Google. You probably get better diagrams. What I want you to know are the layers of the atmosphere, but I'm more interested in the lowest two, the troposphere, and then the next layer is the stratosphere. Those are the ones I really want you to know. The mesosphere, we don't do much in there. The thermosphere is way up high. We're not worried about this. We are looking at the temperature, and so what we're saying is, on average, the temperature decreases in the troposphere, and then when you get ozone, which is a gas that absorbs ultraviolet radiation, and if you should take a look at how to spell the word ultraviolet, you then are absorbing radiation. So we have to understand a few things about the atmosphere. First of all, we change the temperature of an object through methods of transferring heat or transferring energy. So I want you to write this down. I want you to think of heat as a verb. And what I'm saying is, to heat is to transfer energy. Now there's three ways to transfer energy. The first one is radiation. These are electromagnetic waves, visible light, infrared, I-N-F-R-A-R-E-D, ultraviolet. Those are the common ways that we're getting from the sun or the earth that give energy. So if you're getting energy coming in, the temperatures are going to go up as the molecules are moving faster. If you give off energy, then the temperature is going to start to want to go down. So temperature, to the first understanding, is all about the energy coming in versus the energy going out. If more energy comes in than energy goes out, temperatures are going to go up. If more energy goes out than comes in, temperatures are going to go down. So really important that you just get what I just said, and make sure you understand that. That's one of the ways that we're going to be dealing with stuff in this class, is to talk about what's coming in versus what's going out. And there's tons of ways that we do that. It'll make sense as we go into Earth-Sun relationships. Okay, so keep that in mind. Radiation is just one of the three methods of putting heat or energy in or out. Now the other two is called conduction, and conduction is the transfer of heat through contact from warm to cold. So if you were sitting in my classroom, I would say, okay, I want you to do something. I want you to touch something paper. Okay, and then I want you to touch something metal, maybe the leg of your chair or something that's metal. Which is colder? Now most people are going to say, well, the metal's colder, but the reality is they're the same temperature. It's the temperature of your room. What feels colder is the metal, and the reason for that is your hand is warm. When I touch something paper, I am getting heat, energy from my hand going into the paper. Okay, and so I feel it to be somewhat cooler. When I touch something metal, like the leg of my chair or a lamp, or here I've got my microphone over here. I don't know if you can see that. It's metal. It feels colder, and the reason it feels colder is I'm losing energy from my hand into the metal. Metal conducts heat well, so you're going to lose energy much more quickly. So conduction is that ability to transfer energy away from something that's hot. Okay, so conduction is another way of doing that. The last way is called convection. For now, I just want you to define convection. Convection is the transfer of heat within a fluid by the motion of the fluid itself. So you want to think of what's a fluid? Well, a fluid is something that flows. Now, obviously, liquids flow, but we're talking about meteorology. We're talking about the atmosphere, and the atmosphere also flows. Air flows. So if I have warm air on one side of the room and cold air on the other side of the room, if I turn on a fan, I'm going to move the air and redistribute where the cold air is and the warm air. It's going to mix together. And that is called convection. So convection, you should have this well-defined. Pause me if you need to. Convection is the transfer of heat within a fluid by the motions of the fluid itself, okay? Within the fluid. Now, keep in mind, if I'm moving it horizontally, we're going to call that advection, A-D-V-E-C-T-I-O-N. That's what a meteorologist calls that. Well, how do I get air moving? I told you in a room I turn on a fan. I've got a fan behind me, but I don't have that on. But I would move the air. But outside, what do you think the movement of air is called? And the answer is wind. So wind is the horizontal movement of the air. But meteorologists like to think of horizontal motion being different than vertical motion. So to a meteorologist, when I use the word convection, I am talking about air moving up and down. So thunderstorms are what we call convection. So any movement up and down is a transfer of energy. That's convection. If it's sideways, it's advection. And the motion of the air is what's doing it. So review, 3 methods of heat transfer: radiation, conduction, convection. Okay? And anytime I'm transferring heat in, the temperature is going to try to go up. If I have energy going out, the temperature is going to go down. And so what I'm saying at this point is, if more goes in than goes out, so imagine I've got some object, more energy is going into the object than going out of the object, then the temperature will go up. If it's only radiation, more energy coming in than going out is going to cause the temperature to go up. If I have more going out than coming in, then the temperature is going to go down. I'm just going to take a side step here and say, what's temperature? Temperature is the average kinetic, K-I-N-E-T-I-C, energy of the molecules. Temperature is the average kinetic energy of the molecules, which means that the molecules are doing this, they're moving. And if they're moving faster, it's warmer. So that's all we're talking about. It's the energy of motion of the molecules. Okay? So in the atmosphere, what we're saying here, in the troposphere, and the end of the layer is called a pause. So the troposphere is ended at the tropopause. The temperature on average goes down the higher up you go. And there's a reason for that, which we don't know yet. We'll get to eventually. When I go to the stratosphere, I have ozone, which is a gas, and it absorbs certain types of radiation called ultraviolet. And ultraviolet radiation is actually really important for us. We need a little bit of ultraviolet radiation, what gives us skin pigmentation. It gives us vitamin D, which is huge. It's so important to get sunshine. Too much, and we start to burn. Too much burning, and we might get cancer. So we have to protect ourselves from too much ozone. But ozone is also a big deal in killing viruses, because viruses don't survive with the ultraviolet radiation. So in the stratosphere, as I go higher up, the temperatures actually go up. The temperatures are getting warmer the higher up I go. And that's because ozone is absorbing ultraviolet radiation and being stimulated, and the molecules are moving faster and the temperature is warmer. Okay? So in the troposphere, the temperature on average goes down. It doesn't have to always, this is just on average. And then in the stratosphere, the temperatures go up. Now, do you agree that the atmosphere is cooling in the troposphere as you go higher? That's called a positive lapse rate, L-A-P-S-E. A lapse rate is a rate of cooling. Do you agree in the troposphere? It is cooling as you go higher. But what about the stratosphere? Is that going to be a rate of cooling? No, it's not a positive lapse rate, it's a negative lapse rate. And the negative lapse rate means that the temperatures are getting warmer with height. We call that an inversion, I-N-V-E-R-S-I-O-N. So we have the inversion in the stratosphere with a negative lapse rate. Temperatures are getting warmer the higher you go. Troposphere, temperatures are getting cooler the higher you go. In the mesosphere, it gets cooler again, and in the thermosphere, it gets warmer again. So just understand the stratosphere is an inversion layer, and these will come something that we use later on in the semester. Okay, so lots of information right there. So review. See if you can know this. 3 methods of transferring energy. It's called heating. 3 methods of heating. Radiation, electromagnetic waves like infrared, ultraviolet, visible light is electromagnetic radiation. We have conduction, the transfer of hot to cold through contact. Things are touching. And then there's convection, the transfer of energy within a fluid by the fluid motions. If it's horizontal, it's advection. If it's vertical, it's convection. Okay, good. So here is the structure of the atmosphere. Here we're in the troposphere. And all I want you to know is that about 78% of the atmosphere is N2. That stands for nitrogen. It's atmospheric nitrogen. You breathe in, you breathe out. Nitrogen is not being used by your body directly. We're not going to worry about how it's used. But then there's 21% is oxygen, O2. That's what we're breathing. That's what's used for respiration. So I want you to know what are the 2 most important gases of the atmosphere? Nitrogen and oxygen. Now there's a little bit of a gas called argon. We don't care about that. There's a little bit of carbon dioxide, CO2, which plays a role. But nitrogen and oxygen is what matters the most. So we can skip past there. There you go. We also have water vapor. Now water vapor in the atmosphere is gaseous form of water. We know what water looks like. So I'm going to ask this question on a test. So you probably want to write this down and highlight it. Okay? What's the number 1 fact about water vapor that I want you to know? What's the number 1 fact? And the answer is it's invisible. Okay? Now, in classroom, what I would do is like, what's a cloud made of? And people go, oh, it's made out of water vapor. And I go, can you see water vapor? And the answer is no, you can't see water vapor. Can you see a cloud? Well, of course I can see a cloud. So what I'm saying is at this point is a cloud must not be water vapor. I see liquid water. I can see solid water. We call it ice. So a cloud is either little droplets of liquid or ice, but it's not vapor. Now, in the air, there's vapor. And we're going to be doing a whole section on vapor in the air. But the first thing you need to know is that it's invisible. Got it? Good. Now, the atmosphere, when you're in the tropics near the equator, you're talking about 2 to 4% of the air is water vapor. Up in the mid-latitudes, which is where we live, in the middle latitudes in the United States, 1 to 3%. When it's colder, it's going to be less than that. It's also less the higher up you go, and there's something to do with temperature, and we'll deal with this. So here's some questions you can go through just to refresh yourself on this stuff. And we're going to be talking about all these things in terms of variability, blah, blah, blah. Here, this is a section on fire. We're going to do with fire weather, and water is going to matter, obviously, for fires. Okay, now the next thing we do is pressure. Okay, so we can go through this pretty quickly. You're going to be going through this module. You'll be taking the quiz on it, and hopefully these are the really important things that you need to know. Pressure, first thing is, it's the weight of the air above you. The weight of the air above you. Okay, so here's a weird question. Let's see if you know the answer. If I'm standing on the ground, how much air is above me? The answer is, well, all of it. There's no air in the ground. So all the air is above me. When I'm at the ground and all the air is above me, if I were to average it out over the entire planet, it's going to come out to just a little bit more than 1,000 millibars. Over here on the bottom of the screen, it says the unit of pressure is a millibar. Now, it's actually 1013.25 millibars. MB stands for millibars. That's average of the entire Earth. But for the sake of argument, it's about 1,000 millibars. Okay, so write down the 1013.25. Do you know that 29.92 inches of mercury, if you're a pilot, for instance, you might know something about your altimeter is measured in inches of mercury. It can be also pounds per square inch. It's molecules hitting over some area, and that's 14.7. Your car tires is probably 35, 36 psi. Bicycle tire might be 60 psi. So I just want you to know that air pressure is the weight of the air above you. So what happens when you go higher up? Well, there's less air above you, so the pressure goes down. So it's going to decrease with height. Here's talking about barometers, they're talking about variations, high pressure, low pressures, and we get this thing as a function of altitude. Really what I want to do is maybe do something like this. So I'm going to go pressure versus height. And if I just look at images, do you see this image here? It's not straight, it's a curve. It's what we call an exponential curve. So the higher up I go, the pressure drops exponentially. Now we're breathing at about 1,000 millibars of pressure. You get down below 700 and you're gonna have a hard time breathing. So the higher up a mountain you go, the harder it is because you don't have as much oxygen. You go up to 600 millibars and it's not enough and you're gonna start to pass out. Okay, so you need enough oxygen. That's why in an airplane, if you're flying low, you're okay. But if you go high enough, that's when you need, a real good amount of oxygen. You need that cabin to be pressurized. So answer some questions here. We can skip this. Now, what's the driver of our weather? And here's where we get to. We got, it's the sun. The sun is a big ball of gases that are huge amounts of energy is being created through a process known as fusion. You don't need to know that. But it gives off radiation, visible, infrared, ultraviolet radiation, goes to our Earth. And that radiation is the source of our energy. So the Earth sits there and goes, hey, I'm getting this energy, and now my temperature is going to want to go up. But we've talked about radiation, and here's something you need to add to that section over there. Every object with temperature can both absorb radiation and emit radiation. So not only is the sun giving us radiation, but the Earth is also giving radiation off into space. So what I could probably do is show you some radiation graphs of incoming versus outgoing radiation. And I'm going to go radiation of the Earth, or maybe I should spell it Earth. And if I look at images, images are good. Here's radiation coming in and radiation going out. So we have the sun giving shortwave radiation, visible light primarily, and then infrared or outgoing long-wave radiation comes out of the Earth. And it's that balance. If I have more coming in than going out, the temperatures start to go up. If I've got more going out than coming in, the temperature is going to go down. And then we start seeing some interesting things going on, and that's how we're getting to the weather. So again, Google is your friend to make very simple images that explain this nicely. My neighbor is cutting their lawn during my class. This is terrible. So here's energy coming from the sun, incoming shortwave, outgoing long wave. You might know those terms. I'm not too worried about it. So here's the heat balance. Here's the solar radiation. We got a bunch coming in. But notice that the Earth is a big sphere. So the sun, and you got to imagine this like during the day. You're looking up at the sky, and the sun's almost overhead. It's really direct. It's very hot. But when the sun's off at sunset, it's coming in at a low angle, and it's coming in and it's deflecting in or being absorbed, being distributed over a larger area, and it's not as intense. So what happens is we have more energy coming in from the sun over the equatorial regions, but in the polar regions, it's not getting as much. So what I want you to know is this: what is the cause of the weather? The cause of the weather is that the sun differentially heats the Earth because the Earth is a sphere. So you're going to write that down. The poles are cold and the equator is warm, and there's going to be an adjustment in there. Okay? So super important. Now I'm going to show you something that's kind of cool. Here's our College of DuPage satellite page. If you just want to do, if you want to look up College of DuPage satellite, you'll find this link really easily. We call ourselves NextLab, and people all over the world use this site for our satellite imagery. And here's the entire Earth, and what we're seeing is radiation, visible light that's being reflected. So clouds are reflecting a lot, and we're seeing it all white, and the oceans and land are dark because they're absorbing radiation. So notice that at any given time, and if I go over here and stop for a second, notice it's bright over here and it's dark over here. So how much of the Earth is lit at any given time? Half. The sun illuminates half. Notice that that line, and what I can do is this. Let me see if I can work some magic here. First thing I'm going to do is go down here. Use the mouse here. I'm going to call up Epic Pen. Okay, and I'm going to draw a straight line over here. Notice that that line, everything to the right is lit, everything to the left is dark. Well, where's the equator? The equator on here is about here. So there's the equator. Notice that more of the northern hemisphere is lit than the southern hemisphere. And the reason for that is that we're getting seasonal variation because the Earth is tilted. So we have the tilted Earth, and now the sun is shining on the northern hemisphere for a larger portion than the southern hemisphere, because we're in the summertime. In the winter, obviously, it's different. So the fact that the sun is longer time and more direct in something like this tells me, well, I don't want to draw that. It tells me that we get a variation in the year from the tilt that causes seasons. Our summer season is warm, and the reason for that is, on average, we're getting a lot more radiation because the sun is more direct and has longer days. In the southern hemisphere, they're getting into winter, and that's meaning that the southern hemisphere is less intense, less direct, and has shorter days. So the tilt causes seasons, but the weather is because the Earth is a sphere. Hope that makes sense to you. Okay, so I'll keep this guy in case I want it. And that just shows you how this goes. So it's kind of fun. And there's a lot of cool things that I could show you, but I wanted to at least start with that, okay? Okay, so I say this is important that you go through these diagrams and maybe add them to the notes. Just look through them, make sure you've looked in them. So temperature influencing factors. Number one is the solar angle. How intense, how direct is that angle? So I want you to think about this. Imagine that I take a flashlight and I shone a flashlight on the ground, straight down, and I get a circle. Okay, I have so much energy coming out of the flashlight being spread out over this small circle. But now imagine that I turn this flashlight sideways. What happens to that circle is it becomes elongated. I have the same amount of energy coming out, it's spread out more. So the more direct the radiation, the more radiation that's coming in. When it's coming in at an angle, it's being spread out. So that's what they mean by solar angle. The duration, obviously, too. How much energy comes in depends on how long the sun's out. The longer the days, the more incoming energy there's going to be. Now, there's also pollutants and moisture. I'm not going to worry about that. And then what happens to the light when it hits the ground? Well, here's a couple things. The light can be absorbed, and that would make it warm. But light can also be reflected. So the amount of reflection is called albedo. A-L-B-E-D-O. And the albedo says bright surfaces, shiny surfaces, reflective surfaces reflect a lot and doesn't get as warm. Now you should know this. If you're walking on a sidewalk barefoot in the summer, you can probably survive the warmth of the sidewalk. It's warm, but it's not bad. But you walk across blacktop in your bare feet in the summertime, super hot. So white's reflecting, it doesn't absorb as much. Black absorbs a lot, and it gets really hot. Okay, so here's the temperature seasons. What I want you to do is go download this video and take a look at it. I mean, I want you to see if you understand it. There's the Earth tilted, and we have the equinoxes, and we have the solstices here. And they just kind of talk about where that day-night boundary is, which I showed you before. Okay, oops, went way back. What happened? All right, so moving on, we talk about the angle coming up over. So try to figure that out. Try to understand this diagram a little bit. At night, see what happens at night? Well, at night, radiation goes out to space. See, at night, what's coming in at night? And the answer is, well, nothing. So what should the temperatures do at night? You're giving off more radiation from the Earth than you're getting in because there's no sun out. So your temperatures in the night should start to continue to go down. But if it's cloudy, see these clouds here? They're giving radiation back to the Earth. So which is going to be colder, clear night or cloudy night? And the answer is, well, a clear night is going to be cooler. A cloudy night gets radiation coming back down to the surface, so you don't lose it as quickly. So go through here, answer these questions. That would be a good thing to kind of review. We're talking about, here's that word albedo, and they'll give you some other examples. I'm going to go through it fairly quickly. We have a lot to deal with. We have a lot of stuff on weather before we can start applying it to the things that we want to talk about in this class. So you can talk about conductivity. Remember, that's how well does it conduct? What conducts the best? Metal. What doesn't conduct very well? Dry air. Wood. Water is not a very good conductor. Okay, so answer this question. That's a good thing to go through. Don't worry about specific heat, although it, like blacktop, pavement can hold on to that heat. It takes a while. Water is a very high specific heat, means you need to put a lot of energy in before the water gets warmer. Air can get pretty quick. Dry air can warm up really quickly. Water takes a long time. We can go through evaporation. We're going to get to that later on. Condensation, water vapor turns into liquid. See, I'm not supposed to see this. So look at this. Radiation, right? We have absorption, emission, and reflection. Those are what happens. Now, this diagram, super important. So you need to figure out a way to copy this into your diagram that you're going to turn, because I really want you to understand this diagram. And what I'd like you to do is pause me for a second and figure out what each of those lines represent. Okay? Then I come back and say, hey, welcome back. And let's take a look at this. So the first thing is, this is sunrise to sunset. So this dark blue here, this angle here, tells me how much energy I'm getting from the sun. So when do I get the most energy? When the sun is most directly overhead. When is the sun most directly overhead? Noon. Halfway between sunrise and sunset. But this light blue line is the outgoing radiation. Now the cooler something is, the less radiation it goes out. So when it's coolest, it gets less radiation going out. When it's warmest, has the maximum outgoing radiation. I mean, I think that should make sense. But the question is, when is the warmest time of the day? So what I'm going to do here is I'm going to go back to my little pen over here. And I can use maybe gray. I'm going to look over here and say, well, this is this time, noon, when I've got the most amount of incoming radiation. But when is it warmest? It's warmest, let me go over here. it is warmest a couple of hours past noon. So I think on my test, it's going to say 2 to 6 hours after noon is when it's warmest. Now, why is that? At noon, we get the most incoming radiation, right? So you should, this is what you should write down. At noon, we get the most incoming radiation. But for the next few hours, we are still getting more incoming radiation than we're giving off, which means our temperatures should continue to go up. At some point, the incoming radiation, that's this guy over here, right, is going to be going down, and the outgoing radiation, which is the light blue, is still more than the incoming radiation. And what that means is the temperature goes down. So when's the warmest time of day? 2 to 6 hours after noon, because in that time period, I have more incoming radiation than going out. What makes temperatures go up in terms of radiation? Good question to write down. More incoming radiation than going out. I've said that many times. I hope you understand that. Now, when is the coldest time of the day? A lot of people go, well, right before sunrise, and that's not the answer, because the temperature continues to go down at night. Now the sun comes up. The sun, the amount of radiation the Earth is giving off is still more than the amount it gets from the sun, at least for this time period here. Once I get to this time, now I'm at minimum temperature. After about between 30 and 60 minutes after sunrise, I now get more incoming radiation than outgoing on average. The temperatures will start to come back up. So if I want to find a record cold temperatures, I'm looking right after sunrise. That's when it's going to be on a clear night, and I don't even want winds. So that's going to be those really cold nights. And we're going to be talking about cold temperatures and warm temperatures. So you need to know this. This is really important diagram. So I hope that makes sense to you. If you don't, obviously either write on a discussion board or send an email if you want to have virtual office hours or just whatever. I'll try to answer that. But go back and make sure you understand that. Of all the things I've said today, this is one of the most important. Maybe not the most important, but definitely one of the most important. Now, the same is true in terms of seasons. The day that we receive the most incoming radiation, the sun is most direct overhead, it's the longest day of the year, that's the summer solstice, that's June 21st. But July, mid-July, about a month later, is the warmest time. Why? Because between June 21st and the middle of July, I still have, on average, more radiation coming in than going out. And my temperatures still go up. Once I get to mid-July, now on average, I'm going to give off more radiation than I'm going to get back from the sun, and the temperatures start to slowly down. So that's my seasonal variation. But this variation is called the diurnal variation temperature. So I'm going to show you the diurnal variation of temperature. I go to images, and I guess what I want to look at is if I think about temperatures over the course of time, they go down, they go up, they go down, they go up. That is a 24-hour cycle called the diurnal temperature variation. That only means daily. The opposite of daily is nocturnal. You probably heard that word, night, like an animal that lives at night, it's nocturnal. But you get this cycle of temperatures going up. Now, I just happen to want to show you something here. Here's a forecast. I'm doing this on May 29th, so those of you taking in the fall, I did this lecture before. Here's the temperatures forecasted for DuPage. Notice the temperatures go up and down. This is the diurnal cycle of temperatures. Now, come Monday, it doesn't go up quite as nice, so it's probably got clouds or rain in here. And then next week, it's going to be warmer. But that up and down cycle is the diurnal cycle. Over here, this is your seasonal cycle. Coldest in mid-January because the shortest day is December 21st. For the next month, we are still on average giving off more radiation coming in, and the temperatures continue to get colder. Once we get to mid-January, temperatures start to come back up. So there's a little bit of a lag between the most radiation coming in or the least radiation coming in and the warmest or the coldest time of the year. So this is a seasonal variation because the Earth is tilted. This is a diurnal variation because the Earth is rotating. Okay, so really important that you understand this. I hope that makes sense to you. Answer these questions. I think it's important that you get an idea. Then they're going to tie it all together with fuels and all this other stuff. So boom, there's your module, right? This isn't that bad. We kind of went through a good amount of stuff. I'm going to go backwards in this module, and now you'll see the quiz. So you should be able to go through here. You've taken your notes, practice the quiz on MED-ED, and then go take it on Blackboard where it says MED-ED quiz for basic weather. And I would really recommend, if I have lectures, to take the lecture first and then take the quiz. Okay, so you get a background of information. Now I want you to see something else here, okay? Anticipating hazardous weather, chapters 1 and 2. So I'm gonna skip back here because I want to show you this. Here's your introduction. It just tells you some information. I have a worksheet that talks you through it. Please just read it. Answer the questions. It talks about snow. Most of the metro area, 2 to 3 feet. There's 31.8 inches of snow. And what they did, I mean, it's crazy. Look at this. And this is the answer to one of the questions on the thing. Well, what's the most? 87.5 inches of snow. That's crazy. Here's a tornado outbreak. 2011, Mississippi River flooding. So they just tells you about what we're going to be doing in this class, okay? So I go back to the top of the page, and then I go to weather. And notice that in weather, there's a lot of information in here that's very similar to what we did in the basic weather. Hey, look, the sun. The sun radiation reaches only half the planet. We showed you that. The amount of radiation varies. It's tilted. That causes this. So here's the same diagrams, the same videos. Be curious. Tell me, please. There's one of the questions on the worksheet says, be curious, and that's where the answer is. So here's temperatures. Here talks about pressures. Notice these are the same things we've talked about. So you should be able to go through this pretty well. Now you get to the scale of winds, where you get winds, and these diagrams are going to be important. And we're going to deal with this in the upcoming one. But today, that was your sun and your temperature and your radiation weather balance. And that's your basic weather. So again, go back, take these notes, write them really neat. This is your chance to shine. I want to look at this on your work and say, oh my gosh, what great effort. Perfect score. If I go, that's kind of messy, because I'll show you some really good ones. I'll show you what great students do. And you all should be great students. And then I'm going to be able to grade it easily. I'm going to go 100%. And you're going to be happy because your grades are going to be way good, okay? So turn in the notes from this lecture, and that's worth a good sizable part of your class grade. Then you get the MED-ED quiz, and you should be able to do well on those. You can take your time, and now you've really learned independently how to get this stuff. When you take my test, I'll ask questions. Some of the questions might be simple, like what are the 2 most abundant gases in the atmosphere? What are the lowest 2 layers of the atmosphere? What are the 3 methods of heat transfer? And your notes should have everything that you have for that test. Now, there might be some harder questions that check to see if you know it and understand it, but that's okay. Not everybody can get an A, but everybody should be able to do a good job at rewriting the lecture, and there you have it, folks. Okay, so if you have any questions, message board, discussion board, or you can email me, and I'm going to stop sharing my screen, and now I'm going to stop the recording. So have a great day, and I'll see you for the next lecture.